Welcome back, everybody. It's a nice and wonderful spring break season. Too bad you don't have it. Wow. Because you started late, you had a stretched out winter break, and then you rose the spring break. Too bad. It's a trade-off. Let's just take a quick in-class attendance check. Okay. Thank you. Small class today. 5 people in class. Good.
Not wearing a face shield.
5 people in class, 5 people online. That's good. So, people online, if you have any questions, just unmute yourself and then start asking questions. Okay. I'm going to mute all to begin with, but I don't forget you. All right. So hopefully you can see the desktop. Let's just begin. All right. So first of all, updates. Is there any new update? Not really. Okay. So I think phase 2 of the project is going to be announced soon. Once I complete Unit C, which is the performance lecture, you're going to, is that right? Let me double check. When it's going to be next phase of the project? Project phase 2. Project phase 2. Where? Where? Right here. Yeah, that's right. When are you going to do phase 2? Oh, yeah, I can make it do anytime. I realize it now. So when do you think you can do phase 2? Anybody? Yeah, okay. So,
It's only like 2 weeks away.
I guess that's true.
okay, April sometime.
A week and a half.
Okay, yeah. So I think this would probably take some time. Of course, phase 2 is. Now, phase 3 is fairly simple. In other words, phase 3 is based on the phase 2 result. You're going to actually compute the aircraft performance. Performance means actual takeoff distance, landing distance, range, and climb rate, other things. So that is essentially simple computation based off of the optimized design of phase 2. So phase 2 takes some time, okay? So, okay, I'm not going to announce due date yet, but your team shouldn't wait until I announce it, because phase 2 takes some time to complete, okay? So I would say maybe halfway through Unit C lecture, I'm going to announce phase 2 due date, okay? So right now, after the phase 1 completion, you are free to change around your team structure. So if you want to leave your team and join another team, go ahead, do that. You can freely do that in Canvas homepage, okay? So if you're thinking of just restructuring your team, you can do that now, before I announce phase 2. I think Jimmy is thinking of joining SAE, because you and Jessica are working together. By the way, where's Jessica? I
She's
don't see
on an
her.
airplane right now.
Where the hell is Jessica?
She's coming back from
She's coming.
Idaho.
She's in Idaho. Okay. Yeah, I think she mentioned that. Okay, so after she comes back, you can think about it. Okay, because you're taking the same class for other experimental error. You're spending most of the time together. So I think it's a good idea to join in SAE and help a little bit about SAE in progress. Okay. In which I'm the faculty advisor of SAE. I'm not. No, my motivation is not using you to benefit SAE. I think it is very good benefit for you, utilizing SAE opportunity. Okay, so I would highly recommend you considering joining in the SAE. Okay, and who's your current team partners? Jimmy?
David and Robert.
David and, are you here? Robert's not here.
Now he's right behind me.
Yeah, David is here. Are you okay for Jimmy leaving your team?
Robert's right behind me.
Eh?
Robert's right behind me.
Yeah, that's right. You're in class. Not on. Man, it's so confusing. Anyways, so Robert, are you okay releasing Jimmy to Jessica? He said, okay. How about you, David?
Yeah, whatever's fine with me.
Oh, he's fine. Yeah, so both said, yeah, sure, go ahead, take him. Okay, and Jessica said, well, yeah, sure, of course, we're already working together for experimental error. So I think it's probably the way to go, I think. Okay, anyway, so this is the project. So I think now is the time to move on toward phase two. Phase two requires a lot of things. So you're going to actually pick up the best design of your wing to meet your design purposes, and then you're going to try to sort of construct the whole airplane, and then hand calculate to confirm if your aerodynamic properties such as lift and drag matches up against the X prior 5 predictions. That takes some time, okay, and then that is going to form up the entire aircraft to begin with. And then phase 3 is going to be, okay, so now you have an entire airplane sort of optimized using software. Now what is the actual performance? That's the phase 3. And phase 4 is, okay, so let's just take a look at if it's really stable airplane, statically and dynamically speaking. And then you can actually take a look at explore dynamic stability analysis, short term, long term, okay, other things. Okay, so let's just keep moving, okay? So today, let's just get right into Unit C1. We are going to finish up Unit C1, equation of motion. I think we stopped at somewhere in class, we stopped at this page, right? Page 9. Yeah, I think we did example C11. Go ahead,
Are
Jimmy.
you ever gonna go over the exam?
Huh?
Are you gonna go over the exam?
Am I gonna go over the exam? Not really. I posted the solution though. Here's the solution of exam.
Well, will we get our exams back?
Exam is back already in graded file folder.
Oh. Okay.
Yeah, exam is back, so you can see it. You can see the graded work. OneDrive. OneDrive, you have two files. One is submission file. The other one is the graded file. Graded file is read only. Your graded exam is inside of that graded file. Yeah. And then here's the solution. Exam 1, okay? Yeah. So, sure. I guess, look at that, class average is almost 90. 86.67% is class average. I don't think I have to go over it. Everybody did great. No one is failing. That's what I want. Okay. No one's failing. No, nobody's F. Well, this is what the typically be. This is not the error 1. Error 1 is half of the class is F. And then I'm always in a bad mood in error 1 class. Yeah, it's not me. I don't want to. But sometimes I kind of react to it because I give like a MATLAB project in phase 1, which is like a super simple. I can do it like 30 minutes kind of project. And then 4 people doing it, they cannot make it work. And I go, okay, who the hell is your MATLAB teacher? I need to talk to that guy. Kind of. How come you don't know like a .m file? Kind of. I spent half of the time yelling at it. I don't want to do that. Okay.
Good time.
And then sometimes, students actually took my MATLAB class, do everything perfect kind of thing, because that's my way of teaching, and I do the same thing in my aero class. I think Jordan took my MATLAB. That's right. You took MATLAB too. So that actually helps. Those are the group of people actually do the perfect job and have no problem. And other people actually do all sorts of weird things. Just turning into .m file into all of a sudden function without any function header or anything. It just runs, but I have no clue why you do such a thing. And their response is, oh, Dr. such and such taught us to. Huh? I was like, huh? Anyway, this is not aero class. It's just the bringing in that subject and making me kind of mad already. I'm sorry. But let's just move on. Flight mechanics, straight and level and accelerated flight, SLUF, SLUF. This is the starting point of your performance analysis. In other words, airplane is flying straight past, not accelerating. That means lift equal to weight, thrust equal to drag. Very simple situation, okay? So first plot you want to look at is, this is the very first plot. This is called thrust required, thrust available plot. This is kind of thrust plot. Okay? So this is the plot of the thrust plotted against airspeed. So when your airplane is flying the thrust, this is the non-accelerated level flight airspeed. Thrust required, sometimes called TR. Okay? What is this thing? You really need to understand. What's TR? This is essentially drag. Okay? So using X-Flyer 5, you're going to design your airplane, and then X-Flyer 5 will give you this, ideally speaking, how much drag you are going to generate as an airplane. This is the starting point of a performance calculation. So this is how aerodynamically speaking you designed your airplane. Good airplane, of course, have a lower drag, higher lift. Pretty bad airplane have a higher drag, lower lift, of course. This is drag polar, essentially. That's called the thrust required at each corresponding airspeed. Okay? And then thrust available, this is TA. This depends on the propulsion system you're going to choose and install as a propulsion system of your airplane. This is available thrust. Obviously, available thrust must always be bigger than required thrust in order to sustain level flight. Okay, if you need more thrust than available, you cannot maintain level flight. That is going to determine this point. This is the maximum speed you can have for non-accelerated level flight. This is the maximum speed. Because at this point, required thrust is equal to available thrust. You cannot go faster than that. You can temporarily go faster, but you cannot sustain as a level flight unaccelerated, okay? And also opposite end is right here. This is the minimum you can slow down your airplane. Okay, this is a minimum airspeed, Bmin. Now, determining Bmin actually come up with the two conditions. We're going to cover that later. Okay. So this is the thrust plot, thrust available against thrust required plot. Okay. Now, obviously, the difference between required thrust to available thrust is the thrust excess thrust. This is how much excess thrust I can provide for airplane. That excess thrust is going to determine how fast you can climb up, gaining altitude. Okay, it is going to come up later too. Okay, so let's just take a look at. So this is the drag, which is the thrust required. Drag is the thrust required. Okay. So based off of the aerodynamics designed airplane that you spent some time using X-Flyer 5 to come up with how much thrust required does this airplane needs, that is going to be plotted against airspeed. Okay. So this is a straight level unaccelerated flight. So you're going to balance out the forces. Lift equal to weight, and then lift is equal to CL times QS. Q is the dynamic pressure, and S is the wing platform area. Okay. So if L equal to W, you can determine CL, lift coefficient, as the weight of your airplane divided by QS. Okay. And then remember, this is the total drag. This is drag polar. This is thrust required. Obviously, thrust required is a drag. Okay. So this is the thrust required equation. Which is a drag you have. Which is a drag, okay? So this is the thrust required, which is a drag equation. In terms of CDO, this is a parasite drag coefficient or zero lift drag. And then this portion is induced drag coefficient. Knowing that, okay, you are going to expand this equation because Q, you know that Q is equal to 1/2 rho V squared. Okay, so Q is equal to 1/2 rho V squared. So you're going to just plug in this Q into the equation, then come up with this is the thrust required in terms of airspeed. So thrust required, this is D or TR. Thrust required as a function of velocity and velocity. If you plot this function, this is the plot. Okay, so this is called thrust required, which is drag. Okay, so this equation plotted is the thrust plot, thrust required. Okay, this is called thrust required. Okay, so one thing which is quite important is where is the minimum thrust required? That's quite important location. That's where your airplane comes up with a minimum drag coefficient. Let's take a close look at this plot once again, okay? So this is the thrust plot. This is the thrust required curve. There's a minimum spot right here. This is the location of minimum thrust required or minimum drag. Oftentimes, you want to choose this spot to maximize your performance. Not all performance, but some of the performance requires this spot. If your airplane maintains the flight condition with minimum drag, you are going to optimize certain performance of your airplane, okay? Now, this is a minimum drag point in which the location where parasite drag and induced drag composed of half and half. Parasite drag is CDO. Induced drag is KCL squared, right? So this is the location that those two are equal to each other, okay? CDO is equal to K times CL squared. In other words, induced drag is equal to parasite drag. That's where the minimum drag location is. This is the location for minimum thrust required. This is one important thing you should probably know it. Know it means, hey, this is, well, I know this is one of the conditions. Okay. So that's what I'm talking about. Parasite drag is equal to induced drag. This is going to create the minimum thrust required condition, okay? And then speed corresponding to it is velocity at the minimum thrust required point, okay? And then this is the maximum speed in which maximum speed is this one. This is where thrust available, thrust required meet up. This is the maximum speed to maintain level flight. Okay, that's Bmax. And what else? The thrust and the drag curves are not drawn in lower speed. That means minimum right here. So this is velocity minimum point. Okay, so let's just take a look at a little bit more. The thrust and drag curves are not drawn in lower speeds because values of CL that would be required to maintain level flight at low speed exceed the aircraft's CL max. In order to slow down your airplane, typically you want to fly at the CL max location. Typically for airplane, you're going to extend high lift devices, maximum flap down. Let's slow down to the minimum speed. That is essentially your design, your airplane's capability to create CL max. So how much maximum value of CL you can produce is going to determine how slow your airplane can fly. It's essentially aerodynamics, okay? And then this is going to be actually determining your airplane's stall speed. Your airplane stall speed is as low as possible. That's what you want. You want to slow down before your airplane stalls out. So this is the stall speed. Okay? So this is called the stall speed. Stall speed is a function of CL max big time. So that's why you want to have a flap extended when you slow down your airplane. Now, let's take a look at a little bit more nicer detail for those two figures. Actually, there are two possible ways to determine minimum velocity point. This is the case that something called stall or buffet stall and buffet kind of similarity. You know, buffet is like airplane pilots start feeding this kind of thing. It's right before the stall. So stall happens on the verge of buffet. Buffet actually gives you a precursor for the stall. So it's a very bad signal for airplane. Okay, so buffet limit is this is the as low as possible you can fly this airplane. So engine has nothing to do with it. Your airplane's capability of CL max determines this stall or buffet limit. So this is it. So this is minimum velocity is equal to the stall speed. If you go lower than that, you're going to stall this airplane. Okay. The other possible way is airplane design is so good. You have a huge wing and a big, high lift device and all that. You can slow down really, really low speed. But your engine doesn't support it. Your engine thrust cannot support that much lower speed. So this is the thrust limited minimum speed right here. So as an airframe can slow down a little bit more, but your engine cannot sustain the thrust required to maintain the level flight. So your engine cannot slow down anymore. So that actually this is called thrust limited minimum speed. So your airplane is not going to stall at the minimum speed. You can slow down. In other words, you can cut off the engine, turn your airplane as a glider, you can slow down more without stalling. Okay, but it's not going to be a minimum speed. It's called stall speed. Stall speed is much lower than minimum speed. Sometimes your airplane comes up with that kind of configuration. Okay.
To
Yeah.
the left of that minimum, you actually need more engine power to fly slower.
You can sort of say that your engine needs to support enough thrust and lower end speed.
It's very unintuitive.
That's right, intuitive. So typically jet engine, turbojet, and other turbo machine-based engine cannot do that. So this is, commonly speaking, it's just a piston and propeller type of airplane. Okay. All right. So it's just a little bit more detail about this stall speed. So stall speed may not necessarily be minimum speed. Okay. So again, airframe itself or engine airframe configuration, it could be slightly different. Okay. Next page. Okay. So next page, it's kind of confusing. When I was a student, I basically confused up starting from this point. So you're looking at this plot. This is not the thrust plot. This is called power plot. Okay, power. Looking back to this figure, this is our thrust plot. Okay, so this is a thrust or drag against airspeed plot. Okay, now if you're talking about this is the propeller-driven aircraft. If you're talking about propeller-driven aircraft, you actually want to talk about power, not the thrust. Let's be careful. What is power? Power is a thrust multiplied by airspeed. That's the power. Okay, so this is not the drag or force itself. It's a drag or engine thrust multiplied by the airspeed itself, plotted against airspeed. So power is not the thrust. Thrust is not the power, but it's kind of similar concept. If you're dealing with propeller-driven airplane, you want to plot the power rather than thrust. Thrust is for any other type of engines. Propeller-driven airplane, you have to plot the power. Okay. This is actually kind of started to be confused. So let's just continue on. Okay. So first of all, the maximum lift to drag ratio, L over D max, this is the maximum efficiency of the airplane. So oftentimes when you design your airplane in X-Flyer 5, one of the key features is, okay, what is the L over D maximum value? So let's compare 3 airplane wings. Which one comes up with maximum L over D? That is one of the design features. Why do we need such a thing? Okay, so one thing, maximum L over D ratio, lift to drag ratio, in case of straight level unaccelerated flight, which is lift equal to weight, okay, maximum L over D is where the drag is minimum. If you go back to previous page, right here, this is the point L over D max. And then at this point, parasite is induced. Actually, square is missing. Okay? So this is the location where maximum lift to drag ratio happens. Minimum drag. Okay, so let's go back. So you can actually come up with, okay, like I said, parasite drag is induced drag, which is this. Okay? Right. So out of this relationship, you can go further. So at that condition, what is the CL? CL is equal to square root of the ratio of a parasite drag divided by K. This is an induced drag factor K right here. Okay. And also, what is the total drag? Total drag is 2 times either parasite drag or induced drag coefficient. That's the total drag, right? For lift to drag ratio maximum. So L over D is CL over CD. If you plug in those information, you can get the location or condition of maximum L over D ratio is equal to inverse of 2 times square root K times CDO. This is actually quite important equation you have to keep into your mind. You can apply this relationship to determine, okay, so what is the actual L over D ratio for the maximum value for your designed airplane? That's where the drag is minimum. Okay? And then having said that, let's just put your eyes on this plot. This is a power curve. Propeller-driven airplane. So this is not the thrust. So this is the power available for your piston propeller-driven engine. Power is fairly constant. That's what it is. In other words, if you choose to go with propeller-driven airplane, the power generated, which is power available, okay, this is called PA, so PA, is fairly constant value. It depends on what type of engine and propeller combination you choose. This is actually power required based on your drag multiplied by the airspeed. This is called power required. This is the location for minimum power required, right? Okay. So having said that, let's just take a look at it. For a propeller-driven airplane, engine performance is specified in terms of power. You have to, okay? So this is the power required equation. In other words, thrust required. This is the drag multiplied by airspeed, which is drag times airspeed. So this is called power required. Then the airspeed where the power available equals to power required is airplane's Bmax, which is again right here. So this is the Bmax for propeller-driven airplane, right here, Bmax. For straight level unaccelerated flight, you cannot go faster than this value. You have to talk about power if it's piston and propeller-driven airplane, okay? And okay, so now things get confused here. So, okay. So what about turbojet, turbofan powered airplane? We are not talking about piston propeller driven airplane. You are going to also express, okay, turbojet, turbofan airplane in terms of power. Look at this figure. What's this figure? This is the power plot, right? Power plot. This is the power available. This is power required for, this is turbojet jet engine, which is same as this. This is important. Let me repeat. This is, okay, this is a jet airplane thrust required, thrust available plot. You can replot this same exact thing. You just multiply thrust to velocity, drag to velocity, convert this plot into power plot. This is the thrust plot. You can do the same for power plot. So this is the same exact plot in terms of power, not the thrust. Do you follow? Okay, so this is essentially jet engine's power plot. This is the power plot for propeller-driven airplane. This is a jet airplane power plot, which is coming straight from this thrust plot. It's already confusing, but don't lose your focus, okay? All right, good. So this thrust plot, this power plot is essentially the same thing. One is in terms of thrust, one is in terms of power, okay? Yeah, so this is one big confusion I got when I took flight mechanics class in undergraduate level, okay? So now you are going to actually do a power curve for turbojet to turbofan, okay? So one thing you realize, so if you plot the power, obviously the power available is not a constant anymore. Thrust available is constant, but the power available is not a constant. Turbojet airplane, you can accelerate in high speed, okay? So the power actually increase in high speed, which is actually a very good feature of a turbojet engine, but you are going to come up with the location here. Location here is a minimum power, right? This is a velocity for minimum power. Okay? This is the location for minimum power. Let me repeat. This is the location for minimum power required. Let's compare this against this. This is the location for minimum thrust. Is it the same thing? It's not the same thing. So this is the location for minimum thrust or minimum drag, which is not necessarily the location of minimum power. It's not the same thing. This is the location for minimum thrust. Different location. How do you find out this location? There's a method, something called drawing tangential line starting from the origin here. So you're going to draw a straight line that actually touches this power required plot. Draw a straight line which is starting from origin, barely touches your power required curve. That is the location for minimum thrust or minimum drag. So this location, what's the value? 140 something, right? Little bit less, 150-ish. That's the airspeed. That's where the minimum thrust point. Let's compare against this. Is it the same thing? Yeah, right here. Shy less than 150. That's the location for minimum thrust. You can directly lead off from thrust plot because that's where the minimum thrust location is, or you can lead off by drawing tangential line starting from origin, barely touching this power required curve to lead off minimum thrust required point. These 2 points are the same points. Do you follow? Okay, if you lose it, I guess you lose the whole airplane flight mechanics, just like I did when I was undergrad student. I completely lost after that point. Okay, so let's be careful. Those two are not the same thing. Each one of them actually specifies the different performance optimization. Okay, so let's just go ahead and take a look at that. Okay, so this is the location where induced drag is 3 times as great as parasite drag. It's a slightly higher speed than minimum drag point. Let me just emphasize quite important thing here. So this is the location for minimum power. What kind of location is that? This is location CDO is 3 times KCL squared. So this is induced drag is 3 times higher than parasite drag. Or is that opposite? I don't know.
Wait, would it be, what have you
3 CDO opposite, sorry. I had a feeling. Sorry about that. 3 CDO is equal to K times CL squared. So this is the condition for minimum power. How about this condition? Velocity for minimum thrust required. So this is location CDO, parasite drag is exactly equal to the induced drag. This is a condition for this. Okay, so the condition for minimum power and condition for minimum drag or thrust are different. And then airspeed corresponding to it are also different. Let's be careful. Okay. All right. So let's move on next page. Okay. So let's just take a look at example problem C12. Okay. So okay. An aircraft with CDO, parasite drag coefficient 0.020, K1 0.12, and K2 is 0. What's K2? But anyways. So do you remember the drag CD is equal to composed of CDO plus K times CL squared plus one more thing, K2. Let's just take a look at unit B2 or B3, I don't know, B2. Yeah, let's remember those two cases, okay? So depending on your whole airplane configuration, you may come up with two different cases. One is a typical total drag coefficient is a CDO plus K times CL squared, this curve, okay? Suppose depending on your airplane configuration, you may come up with the overall shifting phenomena. CD could be CDO plus K CL squared minus K2. This is K1, if so. K2 CL. So that's this case. You have like a shifting phenomena, and then location of the minimum drag coefficient is called CL minimum D. This is 0.3. So if you come up with this kind of drag quota out of X flyer 5, you have to keep dragging with this K2. Okay? I hope you don't. This is going to dragging all the time, extra factor. But anyway, so this is K1CL minus K2CL, right? So in this case, K1 is 0.12, K2 is 0. Whoa, phew, that's right. Okay. And then H is 30,000 feet, and the Mach number is 0.8. If the aircraft has a wing area of 375 feet square, and it weighs 25,000 pounds, what is its drag coefficient? And then how much drag is it generating? Drag coefficient and also drag itself, okay? If the aircraft is in thrust, straight level unaccelerated flight, how much thrust is its engine producing? If its CL max is 1.8, what is its stall speed at that altitude? Example 5.3, what is the power required for the situation for the example 5.2? So let's just find out, okay? So first of all, let's just find out, okay, standard atmospheric value. Altitude is given 30,000 feet. So you can, of course, look up your property table of standard atmosphere, but if you have that kind of thing in your hand, you can look it up, but the density is supposed to be 0.00089. Unit is a slag per cubic foot, okay? And speed of sound, of course, this is a square root of gamma, RT. With a standard value of temperature here, speed of sound at 30,000 feet should be 994.8 feet per second, okay? So since Mach number is given, you can determine airspeed, V infinity, which is Mach number multiplied by speed of sound. Mach number is 0.8 for this case. Speed of sound, 994.8 feet per second. You are going to give airspeed 795.8 feet per second. Okay, so far? So this is the airspeed. And then let's find out dynamic pressure Q. Q is equal to 1/2 rho V squared. Dynamic pressure of this flight, 0.5 times density 0.00089 slugs per cubic foot multiplied by airspeed 795.8 feet per second square. Okay? So if you compute, you should have dynamic pressure 281.8. This is pound per feet square, PSF. Okay. So from here, you can determine, of course, lift coefficient, right? So lift coefficient is weight over QS. Weight is what? Is the weight is given? Yeah, 25,000 pounds. Weight is 25,000 pounds. Q, dynamic pressure we just found, 281.8 PSF. Wing area, is it given? Wing area 375 feet square, right? What is the lift coefficient? 0.2366. So this is the lift coefficient you're generating to sustain straight level unaccelerated flight. Okay, so far. Okay. So then the drag coefficient. So drag coefficient CD, of course, is composed of CDO, which is parasite, and K times CL squared. This is induced drag. And CDO is given 0.020. K is given 0.12. CL we just found 0.2366. Okay? Square. This is going to give you drag coefficient 0.027. Okay. So from here, how much drag per pound you're generating? CD times Q times S. Drag coefficient you just found 0.027. Q is a dynamic pressure, which is 281.8 PSF. Wing area 375 feet square. Drag is 2,823 pounds. Okay. So the question is, if the aircraft is in SLEF, standard level unaccelerated flight, how much thrust you need? Anybody? That's right. This is exactly what you need for thrust. Thrust, which is the thrust required. Thrust is equal to drag, right? Yeah. So thrust required is equal to essentially drag itself, which is 2,823 pounds. That's it. So this is how much thrust you need to sustain level flight and accelerate it, of course. And then if the CL max is 1.8, what is its stall speed? If you have a CL max which is equal to 1.8, what is the stall speed? V stall is essentially square root of 2 times weight of the airplane, rho times area S times CL max. So V stall is square root of 2 times weight of the airplane, 25,000 pounds. Density of 30,000 feet, altitude 0.00089 slugs cubic foot. Area, wing area is 375 feet square. CL max given 1.8, is it? 1.8, okay. If you compute, the stall speed is going to be 288.5 feet per second. This is the stall speed. Typically, minimum speed, you can slow down your aircraft, okay? So this is a very simple application of airplane's, first of all, performance for minimum drag situation here, and also stall speed computation. And now, what's 5.3? What is the power required for the situation in example 5.2? So how much power required for this? Yeah, okay, solution 5.3. So power required is PR is equal to thrust required multiplied by the airspeed, which is essentially whatever the drag you have multiplied by V infinity. So let's just do that. 2,823 pounds multiplied by multiplied by what? What is V infinity? This one is 795.8, right? Right? Because this is the flight airspeed. Okay. So let's just multiply with 795.8 feet per second. So this is going to be the power required to sustain this level flight. This is 2,247,000 foot-pound per second. If you convert it to the horsepower, you just divide by 550. Okay, this is like 4,084 horsepower. Man, this is a huge power required. This is the power required for the engine to sustain this level of flight. Obviously, you need 4,000 horses. Dr. Ashford's got only 2 horses. It's not enough. He needs to bring 3,980 and 3,998 more horses. Anyways, so this is a basic computation. Next page is, suppose if you change your flight condition, what happens to this curve shift? Curve shift is, this is the drag polar. So suppose if you extend gear or speed brakes while you are in flight, what happens to the drag polar? Now, obviously, you are going to increase overall drag penalty by doing such a thing, right? And then that is going to be more severe on high speed. So suppose if you're flying really level straight in high speed, all of a sudden you're dropping landing gear. Of course, you're going to increase the drag big time. This is actually not a joke. You know, U-2 spy plane, that airplane comes up with such a low value of induced drag coefficient. So in order to decrease the altitude, they need to drop down the landing gear at high altitude. That's not joking. You have to drop the landing gear to slow down and lose your altitude because induced drag coefficient is so small. Okay. This one, suppose your airplane comes with a higher weight, increasing the payload and weight of the airplane. What happens here? Obviously, it is going to be severe on low speed and you're going to increase the drag, of course. But in high speed, it's not so bad. Okay, you can say that. The other one is if your airplane flying higher altitude, you know, the increased altitude, what happens is, first of all, the engine is not going to produce the same amount of thrust. So the thrust drops off at the higher altitude, obviously. Your engine is not going to provide the same thrust at the sea level. But at the same time, the whole thing shifted to the right. So as a result, you're going to actually increase the highest maximum speed you can sustain on level in higher altitude. You can say that, okay? So those are the curve shift effects. This is like increasing parasite drag. All of a sudden, you're not changing the K for induced drag coefficient. So in other words, all of a sudden, like extending landing gear or speed brakes, and you're going to dramatically increase the parasite drag coefficient intentionally. This one is you're going to actually increase your payload and all that. Okay, today is a hot day. This is Denver airport. Can we include like those 10 more passengers or not? The decision depends on today's situation. Like what's the temperature? What's the air density? And then, okay, so those are the kind of things you have to keep that into account. So this is drag polar increase, shifting toward up and right. This is high altitude. Okay. So we are going to move right into unit C2 because now we are going to pick up thrust and the power curve and then find out the minimum location of lift to drag ratio and minimum location of power. And then if your airplane maintains that the minimum lift to drag ratio or minimum power condition, what kind of performance you are going to optimize? Glide. If you're doing glide, how far you can glide off. That's the maximum glide range. And then if your airplane doesn't have an engine, it's called a sailplane. What is the minimum sink rate? Minimum sink rate, if it's lower than updrifting of air, you can stay up in air all the time. You don't need engine. It's called sailplane. And then regular airplane, either piston, propeller type of engine or turbojet or jet engine. What is the range? What is the endurance? And then in order to maximize range, what is the condition? In order to maximize the endurance, what is the condition? Those are all different. Okay? So stay tuned, okay? So unit C2, we are going to take a look at the power of glides to begin with. Next is climbing. Of course, the climbing and also seating maximum altitude you can reach. The thrust, which is engine, so propulsion system you choose is going to be a big factor, of course. If you have a light-weight airplane combined with a very powerful engine, you have a really high climb rates. Okay? But at the same time, is it your optimum decision? I don't know. So again, everything is trade-off. And then range and endurance. What is the condition for those to maximize range and maximum endurance? By the way, maximum range is the maximum distance you can travel. Maximum endurance is how long you can stay in air. Those two are actually very different. Okay, so let's be careful. Those will be on the exam guaranteed. I don't have to guarantee, that must be on the exam. Okay, so let's just take a look at, first of all, power of glide. This is the situation of power of glide. So you are going to go back once again, equation motion, okay? So this is the flight path. Flight path angle is airplane's flight path measured from horizon. This is gamma, flight path angle, okay? So this is the equation motion simplified for power of glide. Of course, the thrust is equal to 0. Power off, okay? So you're just talking about gliding. So aircraft flight path angle gamma is taken as positive downward and the thrust is equal to 0. Then you can simplify your equation motion taken in parallel direction in the flight path and perpendicular direction of the flight path. Both come up with those two equations. Okay, so this is called power of glide. So first important thing is maximum glide range. In order to maximize your power of glide, of course, you're going to choose obviously lift to drag ratio maximum. This is going to optimize glide. Oops. Optimize glide ratio, in other words, range. Here we go. This is called glide ratio. In other words, how much range you can fly by sacrificing this much altitude. Okay? So optimized glide range is, of course, optimized range. Okay? In order to achieve this, obviously, lift to drag ratio maximum as you run from unit C1, this is the condition. Parasite drag is equal to induced drag. This is the condition for the maximum power of glide range. Okay? So how about minimum sink rate? Minimum sink rate is the velocity in downwards direction. You want to have it as small as possible. If you happen to have an updrifting velocity of air at that location, which is bigger than sink rate, your airplane can actually gain altitude without engine. This is called sailplane, okay? So minimum sink rate is something you really, really want to know for such a situation, okay? So this is different from maximum glide range. Let's be careful. Maximum glide range. This is the condition, minimum drag point. L over D is maximum. Minimum drag or minimum thrust required, which is parasite drag is equal to induced drag. This is a condition, but in order to minimize sink rate, that is minimum power required point, which is, this is the condition. Oh my goodness, this is the source of confusion. So in order to maximize the range, you need to have minimum thrust required point. In order to minimize the sink rate, you need to have a minimum power point. What are those two? Let's just go back once again. I'm talking about those 2 points. Those 2 points. Now this is the minimum power point. This is the condition. This is the minimum thrust point. This is the condition. Or this is minimum drag condition. This is the condition. Those two are different. This is going to minimize the sink rate. This is going to maximize the glide range. Okay? Guaranteed that this is going to be on the exam. Let's take a look at example here. Okay. Example, an aircraft with a drag polar CD is given 0.012 plus 0.2 CL squared, has a wing area of 698 feet square and a weight 40,000 pounds. what is its lift to drag ratio maximum, and at what speed in feet per second and knots is this achieved in standard sea level condition? What if the aircraft weight decreased to 30,000 pounds? Let's just take a look. Okay, so this is the situation that the drag polar is given as a simple function CD is equal to CD0 parasite plus K times CL square, which is given by 0.012 plus 0.2 CL square. Okay? So first, let's find out what is L over D max. Remember, L over D max can be given by this equation derived in previous unit, inverse of 2 times square root K CD0. Let's take a look at note C1 and make sure we got this equation. So this is L over D max value is equal to 1 over 2 times square root K times CDO. Where is that equation? This equation. Okay. All right, so this is equation 525. So let's just find out. So this is 1 over 2 times square root K is 0.2, CDO is 0.012. This is going to be 10.2. So this is L over D max. This is, by the way, essentially best glide ratio 2. In other words, R over H max is essentially L over D max, which is 10.2. Okay. This is going to give you the longest range of gliding. Okay. Now, the condition to achieve this is basically CDO is equal to K times CL squared. In other words, this is the condition to achieve this L over D max. Parasite drag is equal to induced drag coefficient. Okay. So from here, you can determine how much CL you are actually producing. CL is equal to CDO over K. So if you plug that in, 0.012 divided by 0.2. So CL is 0.245. Okay. So this is a lift coefficient for the condition of maximum lift to drag ratio or maximum optimum glide ratio. Okay. Note. Okay. So let's use lift is equal to weight to solve for the actual speed. You cannot do this actually, by the way. You know why? Because this is not the level flight at all. In exact sense, you cannot say lift equal to weight unless you are given like a flight path angle. In this case, flight path angle is not given, so we cannot find out actual lift. But, okay, let's assume flight path angle is small because you're trying to optimize the range. In other words, flight path angle is as small as humanly possible. That's what you're flying. Okay, but in exact sense, flight path angle is not 0. So this is only an approximation. Okay, let's be careful about that. This is approximation in big time, but fairly close to the reality because flight path angle is very close to 0 anyways. Okay. Let's note that. So if you do such a thing, CL is approximately weight over QS, assuming that the flight path angle is very close to 0. So let's just find out. This is W is equal to W over 0.5 rho B square S. From here, what is the velocity B? Velocity B is square root 2 times W over rho times S times CL. So let's just plug in. What is the velocity corresponding to this condition? 2 times airplane weight, 40,000 pounds. Density sea level, 0.002377. Standard sea level density slugs per cubic foot. Wing area 698 feet square. CL 0.245. This is going to give you 443.6 feet per second. Let's just convert knots. 1 knot is 1.69 feet per second. So you are going to convert it to the knot. This is 262.5. This is a knots in equivalent air speed. 262.5 KEAS, knots in equivalent airspeed. Equivalent means we're using standard sea level density, that's why. Okay, this is the standard sea level density. All right. So suppose if the airplane's weight is reduced, what happens? Any guess? Do you need to fly faster or slower to maintain the same optimum glide angle? Any guess? You fly slower. If W 40,000 pounds is going to be reduced to 30,000 pounds. What is the airspeed? So the weight of the airplane does not affect anything on the lift coefficient. It only affects on the different weight. So you have 2 times 30,000 pounds. Still the same density, 0.002377 slugs per cubic foot. Still the same wing area, 698 feet square. And then lift coefficient is unchanged, which is 384.2 feet per second. The same conversion apply, 1 knot, 1.69 feet per second. This is going to give you 227.3, again, KEAS, knots in equivalent airspeed. Okay. All right, so this is just a very simple computation. This is the optimum glide range. And then do we have an example 5.5? Do we have time? Yeah, that's example 5.5. This is a sailplane's, oops, 5 more minutes. We can do it in 5 more minutes. A sailplane's drag polar is given. It has a mass of 500 kilogram and a wing area of 20 meters squared. What is its maximum glide ratio and minimum sink rate at sea level, and at what speeds are these achieved? Let's do it in next class. I can't do it. Sorry, this is like an entire next page. So, okay, let's stop here today. Next class. Okay, I'm sorry, it's not going to be 5-minute solution. So we are going to pick up from example 5.5 next week, Tuesday. Let's stop here today. Do you have any question? Have a great weekend and see you guys back on Tuesday.